This is the video for Part 2 of Section 3.2, Basic Properties of Rings. We're going to start by discussing subrings some more. So in Theorem 3.2, in Section 3.1, we showed that we only have to verify 4 properties to show that a subset of a ring is a subring, as opposed to all 8 ring axioms. The next theorem shows that we actually only need 2 properties, and this is Theorem 3.6. So let R be a ring and let S be a non-empty subset of R that satisfies the following 2 properties. And we're going to denote these SR1 and SR2 for subring. So SR1 is closure under subtraction, and this states for all elements A, B, and S, A minus B is in S. So we're saying that the set S is closed under subtraction. And then SR2 is closure under multiplication. For all A, B, and S, A times B is in S. Then S is a subring of R. For the proof, to prove S is a subring, we can show that S satisfies properties 1 through 4 of Theorem 3.2. We'll verify the properties in the order 2, 3, 4, and 1. So we'll do 1 last. So starting with property 2, we need to verify closure under multiplication, which will state for all A, B, and S, A times B is in S. Well, this property is identical to property SR2, so since we're supposing that S satisfies SR2, then S will satisfy property 2 here. Next we have property 3, which is the containment of the additive identity. So this says that 0 sub R belongs to S, or that our subset S contains the additive identity for our ring. Now, since S is non-empty, that's part of our hypotheses in the theorem, then there exists an element A in S. By property SR1, which is closure under subtraction, since A is in S, then A minus A is in S. Well, since A minus A is 0 sub R, this implies 0 sub R is in S. And therefore S satisfies property 3. Okay, next we want to show property 4, containment of additive inverses. For each A in S, the additive inverse minus A is in S. So we'll suppose A is an arbitrary element in S. We need to show minus A is in S. Since, as we've shown, 0 sub R is in S, and A is in S, then by property SR1, closure under subtraction, 0 sub R minus A will be in S. Now since 0 sub R minus A is just minus A, this implies minus A is in S. And that's what we needed to show. Therefore S satisfies property 4. Now finally, we need to prove property 1, which is closure under addition. For all A, B, and S, A plus B is in S. So we'll suppose A and B are arbitrary elements of S. We need to show A plus B is in S. Since, as we've shown, S satisfies property 4, then B is in S implies minus B is in S. Then by property SR1, our closure under subtraction again, A minus minus B will be in S. So A is in S, and we've now concluded that minus B is in S, so their difference, A minus minus B is in S. Now since minus minus B is equal to B by Theorem 3.5 Part 3, then A minus minus B is A plus B. And hence A plus B is in S. And therefore S satisfies property 1. Since S satisfies properties 1 through 4, it then follows from Theorem 3.2 that S is a subring of R. So this makes it much easier to verify that a subset is a subring. We just have to show that it satisfies these 2 properties, SR1 and SR2. Next, we want to discuss units. So if a ring has a multiplicative identity, then we can consider elements which have a multiplicative inverse. And so here's our official definition. An element A in a ring R with identity is called a unit, provided that there exists a U in R, an element U in R, such that A times U is equal to 1 sub R, and U times A is equal to 1 sub R. So in this case, the element U is called the multiplicative inverse of A, and is denoted with our standard notation for multiplicative inverses, A with a -1 superscript. So an element in a ring is a unit provided that it has a multiplicative inverse. For an example, first note that every non-zero element in a field is a unit. By definition, a field satisfies axiom R12, which is existence of multiplicative inverses, which states for each element A in F, A not equal to the zero element, there exists an element X in F such that A times X is equal to 1 sub F. Therefore, each element in F is a unit. For another example, note that the only units in the integer z are 1 and -1. These are the only two elements in z, the only two integers, which have multiplicative inverses. So the multiplicative inverse of 1 is just itself. The multiplicative inverse of -1 is itself. For another example, the units in z sub 10, the integers mod 10, are 1, 3, 7, and 9. And we proved in theorem 2.10 in chapter 2 that the congruence class of A in Z sub n is a unit if and only if A is relatively prime to n. So since 1, 3, 7, and 9 are the only integers among 1, 2, 3 up through 9 that are relatively prime to 10, then these are the only units in Z10. And we can use exhaustion to find the inverses of each. So 1 times 1 is 1, so 1 to the inverse of 1 is just itself. 3 times 7 is 21, which in Z10 is 1. So the multiplicative inverse of 3 is 7, and the multiplicative inverse of 7 is 3. And finally, 9 times 9 is 81, which is equal to 1 in Z10. So the multiplicative inverse of 9 is itself. For another example, let's let M sub 2 of R be the ring of 2 by 2 matrices with real number entries. So then a matrix A with entries A, B, C, D with AD minus BC not equal to 0 is a unit with inverse given by 1 over AD minus BC times the matrix with entries D minus B minus C and A. So AD minus BC, as you are no doubt aware, is the determinant of that 2 by 2 matrix. And so A inverse is obtained by dividing by the determinant, and then we swap the diagonal entries, and we take the negatives of the off-diagonal entries. Units in a matrix ring are called invertible matrices, and we can prove this. But first note that the ring M sub 2 of R has multiplicative identity. The identity matrix has entries 1, 0, 0, 1. And so let's suppose that A equal ABCD is an arbitrary matrix in M sub 2 of R with determinant AD minus BC not equal to 0. Then if we take the product of the matrix A, ABCD, times our proposed inverse, this will be 1 over AD minus BC can just be left out in front of the matrix, and then the entries after we multiply our two matrices together are as shown. And this will be the identity matrix. And taking the product of the two matrices in the opposite order, this will be, again, 1 over the determinant times the matrix shown, and this will be equal to the identity matrix again. It follows then that A is a unit since it has a multiplicative inverse with inverse shown. Next, we want to discuss zero divisors. So a commutative ring R with multiplicative identity 1 sub R not equal to the additive identity 0 sub R is an integral domain provided that it satisfies the additional axiom. This is R11, the zero factor property. For all A, B, and R, if A times B is 0 sub R, then A is 0 sub R or B is 0 sub R. Now the zero factor property does not hold provided that there exist elements a, b, and r such that a times b is 0, but a is not equal to 0 and b is not equal to 0. So if we just take the negation of the zero factor property, it's going to say that there exists elements a, b, and r such that our hypothesis ab equals 0 is true, but the conclusion is false, so that both a and b are not equal to 0. Now an element a or b satisfying this condition is called a zero divisor. So here's the formal definition. An element a in a ring R is a zero divisor provided that first, a is not equal to 0 sub r, so it's not 0. And 2, there exists a non-zero element b in R such that either a times b is 0 sub r or b times a is 0 sub r. Now note that if a is a zero divisor, then the element b in the definition is also a zero divisor. Now, according to the definition, an integral domain is a commutative ring with identity 1 sub r not equal to 0 sub r, which has no zero divisors. So that's another way to describe an integral domain. For an example, in Z sub 6, the elements 2, 3, and 4 are all zero divisors. And we can see that since 2 times 3 is 0, and 2 is not equal to 0, and 3 is not equal to 0, then according to the definition, 2 and 3 are both zero divisors. Since 3 times 4 is 0, and 3 is not equal to 0, and 4 is not equal to 0, then 4 is also a zero divisor. If we let F be a field, and M sub 2 of F be the ring of 2 by 2 matrices with entries in F, then a non-zero matrix A with entries A, B, C, D in M sub 2 of F such that AD minus BC is equal to 0 sub F, this will be a zero divisor. So this is saying that a matrix with zero determinant will be a zero divisor. And so if we suppose that A equal ABCD is an arbitrary non-zero matrix in M sub 2 of F with zero determinant AD minus BC, since A is a non-zero matrix by our assumption, then at least one of its entries, A, B, C, or D, is non-zero. And then the matrix B, which has entries D, minus B, minus C, and A, is also non-zero, because again, at least one of its entries is non-zero. And since A times B is the product of those two matrices, and this will be the matrix with entries shown, and on the diagonal entries we have the determinant, which we're assuming is 0. On the off-diagonal entries we have zeros. So this will be the 2 by 2 zero matrix with all entries 0. And this tells us that A is a zero divisor. Okay, so A is non-zero, B is non-zero, and the product AB is 0. Okay, next we want to consider some results exploring the connection between integral domains and fields. So we'll start with theorem 3.7, which is a cancellation law in integral domains. And so this is for a multiplicative cancellation property. So this says that cancellation is valid in any integral domain R. So if we suppose R is an integral domain, then for all A, B, C in R, A not equal to 0 sub R, if AB is equal to AC, then B is equal to C. Okay, so earlier in the section we had a cancellation law for sums, and so this is a cancellation law for products. And so this is saying if we have the same factor on both sides of an equation, we can cancel off that factor, assuming it's non-zero, and assuming we're in an integral domain. So for our proof, we'll suppose A, B, C, and R are arbitrary elements with A not equal to 0 sub R. We'll suppose our hypothesis that AB is equal to AC, and we need to show our conclusion that B is equal to C. Now since AB is equal to AC, then AB minus AC will be equal to 0 sub F, so that A times the quantity B minus C is equal to 0 sub F. That's using our distributive law. Now since R is an integral domain, it satisfies the zero factor property. So this implies we have a product of two elements equal to 0, so this will imply that one or the other of the two factors has to be 0. So A is equal to 0 or B minus C is equal to 0. Now we're supposing that A is not equal to 0, so it must be the case that B minus C is 0. And therefore B is equal to C as required. Now in proving this theorem, we started with the hypothesis AB equals AC. And now you might be tempted at this point to multiply both sides by the multiplicative inverse of A to cancel A on both sides of this equality. And that would give us B equals C if we're allowed to do this. This is not valid, however. In this theorem, we're supposing that R is an integral domain. And so we know that R satisfies the zero factor property, but it need not satisfy axiom R12 so that it may not contain multiplicative inverses of its elements. So we may not have a multiplicative inverse for the element A to multiply on both sides of the equation to begin with. For an example, first note that cancellation is not necessarily valid in a ring which is not an integral domain. For instance, in Z6, 3 times 1 is equal to 3, and this is also equal to 3 times 5. So 3 times 5 is 15, and mod 6, that will be equal to 3. But obviously 1 is not equal to 5. Okay, so we rely very heavily upon the fact that R is an integral domain in order to prove that cancellation property. Next we have theorem 3.8, and this says that every field F is an integral domain. So to prove this, we'll suppose F is an arbitrary field. We then need to show that F is an integral domain. Now by definition of a field, F is a commutative ring with identity that satisfies axiom R12, the existence of multiplicative inverses. To show that F is an integral domain, we need to show that F satisfies axiom R11, the zero factor property. So for all A, B, and F, if A times B is 0, then A is 0 or B is 0. So we need to prove axiom R11. Now in symbolic form, we need to show for all A, B, and F, A times B is equal to 0 implies A equals 0 or B is 0. And using the logical equivalence, P implies Q or R is logically equivalent to P and not Q implies R. This statement is logically equivalent to, for all A, B, and F, A times B is 0 and A is not equal to 0 implies B is equal to 0. So to prove the zero factor property, we're going to prove this equivalent statement. So we'll suppose that A, B, and F are arbitrary elements. We'll suppose A times B is 0 and A is not equal to 0. That's the hypothesis in the equivalent statement. And we need to show that B is equal to 0. Now since F is a field and A is not equal to 0, then A has a multiplicative inverse. Multiplying both sides of AB equals 0 by A inverse, we obtain A inverse times the quantity AB is equal to A inverse times 0. And using the associative law of multiplication, we can rearrange parentheses on the left side. So this will be the quantity A inverse times A times B. And on the right-hand side, A inverse times 0 is equal to 0. That's by theorem 3.5 part 1. So we're using R7, which is the associative law of multiplication, and theorem 3.5 part 1. And on the left-hand side now, A inverse times A is going to be the multiplicative identity, 1 sub F. So that's by axiom R12. And on the right-hand side, we still have just 0 sub F. And finally, 1 sub F times B is just B. So that's by axiom R10. And so we've shown that B is equal to 0. So therefore this proves the logical equivalent statement, which shows that F satisfies axiom R11, so is an integral domain. Now the relationships among the various types of rings can be illustrated by a Venn diagram. So we'll just start with a rectangle, and this is supposed to represent the set of all rings. And rings are either non-commutative or commutative. They either satisfy axiom R9, the commutative law of multiplication, or they don't. So we can basically divide up our set of rings into two pieces. One piece non-commutative rings, the other piece commutative rings. And then rings either have a multiplicative identity or not. And so we can go ahead and throw in an oval here to represent the rings with a multiplicative identity. So those are the rings with a multiplicative identity are inside the oval, and then the rings without that do not have a multiplicative identity are outside the oval. And now a ring with identity may be commutative or it may be non-commutative, just as a ring without an identity may be commutative or may be non-commutative. And then inside the rings with identity, on the commutative side, we'll have the integral domains. So integral domains are commutative rings with identity, which also satisfy the zero factor property. And now we just got done proving a little while ago that every field is an integral domain, so the fields will be inside the integral domains. And so this is where the rings that we've introduced in this course are going to fall. Now, there are still other types of rings which we're not going to discuss in this course. For instance, a division ring is a ring with identity 1 sub r not equal to 0 sub r, in which every non-zero element has a multiplicative inverse. A division ring differs from a field only in that it is not necessarily commutative. And so you can sort of figure out for yourself where the division rings would fit in this Venn diagram. Now, the converse of theorem 3.8 is not true. So every field is an integral domain, but not every integral domain is a field. For instance, the set of integers z with the ordinary integer addition and multiplication is an integral domain, but is not a field. We do, however, have the following partial converse of theorem 3.8. And this is theorem 3.9, and this states that every finite integral domain is a field. So not every integral domain is a field, but the finite ones are. So to prove this, we'll suppose R is an arbitrary finite integral domain, and we need to show that R is a field. And to show this, we need to show that axiom R12 holds, so that each non-zero element in R has a multiplicative inverse. So let's suppose that A1, A2, down through A sub n are the distinct elements of R, so that R is the set containing those elements. And let's suppose that A sub t is an arbitrary non-zero element of R. So we need to show that A sub t has a multiplicative inverse. So we need to show that there exists an element u in R such that A sub t times u is equal to 1 sub r. So let's consider the end products obtained by multiplying A sub t times each element in the ring. So these will be A sub t times A1, A sub t times A2, all the way down to A sub t times A sub n. Now we claim that these products are all distinct. To show this, we can use a proof by contradiction. So let's suppose that two of these products are equal. Say A sub t times A sub I is equal to A sub t times A sub j for some I and j, I not equal to j. Since R is an integral domain, then the cancellation property holds. So this equation implies that A sub I is equal to A sub j. We can cancel the A sub t off. And remember now, we're assuming that A sub p is non-zero. So this is a contradiction which proves the claim. So those products, A sub t, A sub 1, down to A sub t, A sub n, are all distinct. Since the n products are distinct and R has exactly n elements, then these products must be all the elements of R in some order. In particular, one of these products must equal the multiplicative identity of R. So we know that R has a multiplicative identity, so one of these products, A sub t, say A sub t times A sub k, is equal to the multiplicative identity 1 sub R for some k between 1 and n. This implies that A sub k is the multiplicative inverse of A sub t. And therefore each non-zero element of R has a multiplicative inverse, and thus R is a field. Okay, and this completes section 3.2.